All right, so how you guys doing today? Doing good? You have a lot of finals? Yeah, okay, sorry. So you guys know the final exam is the Canvas Online, right? Okay, so make sure you go watch the syllabus on the modules menu. You have a time and date and time for the Canvas Online final exam. And then, yeah, so not much a thing for, not much pressure on the memorizing the rules and everything, but if you just keep watching the exam 1 and 2 review session already, and also I'm gonna hold the review session hopefully this Friday and Monday twice. Mainly I'm gonna go over the new chapters we've been learning after exam 2, but meanwhile you can still watching the exam 1 and 2 review session or the post on YouTube channel. Would be great, but still it's online exam, so meaning it's open book test, so you don't have to really memorize, but you just know how to solve the problem. Okay. All right. So there's this one. This is another. This is actually what we did before. I believe it's Monday. Okay. So what you need to do is whenever you have the hydride coming into here, you're gonna have this negative charge over here, and then when it's back in there with another hydrogen here, you're gonna have this chloro group will leave. Okay, so basically the bottom line. Sorry, E3. So bottom line here is you're just going to have remove this one, and then you're gonna have protonated the carbonyl groups, so will be reduced. So will be just this one. Okay, this is the one reaction we did on Monday. Okay, so let's keep this in your mind, and we'll do the similar reaction over here. So. So let's do the same acid halide compounds over here, and we're gonna actually we're gonna use the Grignard reactions over here. So just try to recall what we just did for the lithium aluminum hydride, but for this one. The simple trick you can do is now we're gonna put this one with, this is your R magnesium X bromide here in this case. So we have this one, and then you actually need to do the similar thing what you did for previous one. This is the product. So only difference from the previous one is you keep this protonated carbonyl group over there. Instead of the hydrogen, you actually adding R groups on your Grignard reactions. Okay. So if you look at this one over here, which is your R methyl group, add it twice over here by replacing this one to the hydrogen group. And also in chain reaction, we'll go to have the leaving groups. So basically, you just need to have the chromol to leave, and then just switch this one to the hydrogen group with the 2 R group added on here. Okay. So that's the trick. So can you guys try this one? But let's change this one to ethyl group. Maybe can you try this one? Okay, but so yeah. So compare this one. So you just need to remove the relieving groups. I'm gonna put this one on here actually with the proton because of the hydrogen cation. But you just need to add two R groups, two ethyl groups on here. This is the. Yeah. Can I move on? You wanna do one more? Can I move on? All right, then. Okay, here's one more thing I want to mention before we move on to the next one. Is diorgano. A reaction over here. So this is the. Do you guys remember this one? This is what we did in the previous chapter with the Gibbon reactions. So what it does is they actually approach to in this way. In this way, and that makes the push and push down. So negative charge neutral and goes to B. So then this way. Okay. And then this bond move on to one of them. So even though there's a 2R prime, you only get to have a 1R on this side in the carbonyl groups. So that's why you have the other copper with the other R group of leaf as a leaving groups. So you have ketone. Okay. Okay. So let's try the problem. Let's try this one real quick. So only thing you have to do, you have two R groups over here, right? And just make sure you're putting only one R, making this chroma group to leave. That's it. Okay. So if you look at this one, it's in halotype form. Try to get that chloro group to leave, and just put one R or your dot organic copper to there, so it can have a product. Okay. Yeah. So, yeah, you only need to focus on this part over here. So once again, I'm just gonna leave this one away. This is a leaving group. But as we saw before, sorry. So as this one approaches to here, switch only one R there, right? So it will be this one. Because it goes to push on here, gone, without that one still, so we're keeping the same. This will be added on the other side by making the chroma groups to just chloro group to leave. Makes sense, right? You want to do one more? Okay, just do one more. Okay, how about this one? This one. So which way? maybe 10 seconds. Okay, so yeah, so I'm gonna remove this one. Okay, and I'm gonna put there are two, but I'm gonna put only one methyl group. So yes. Okay, good. All right, so let's move on. Alrighty, the next one is the how you can make some anhydride compounds. Okay, that's an anhydride compound. So this is one example. If you have some carboxylate, so this is the sodium acetate, some ether base. So what it really means is pretty much the same, but we used with a different type of carboxylic acid derivative compounds. So if you look at this carbon over here, okay, so this carbon is in the carbonyl groups with a very strong bond to the oxygen here, and also electronegative the halogen groups over there too. So this is a very good target for one electrophile. So nucleophile. So this is sodium acetate. This part will be very good, right? This is good nucleophile. It goes to there. Okay. So when it goes there, they'll be. I'm not gonna say every time I do this, but go up and down. So negative, single, double, coming down. It's very common. And then push will go down to here, and they can make it to leave. This one. But chloro obviously have a very electronegative elements. They take this full electron. Okay. So then you have to have this one bound to here, right? And there's the other side is this. Okay. So you form what? You form acetic benzoic anhydride. Okay. Does it make sense? So whenever you have a carboxylate groups with salt form, like with some cation, use that. So carboxylate compound with some salt, a metal cation. You only need to get this one to there and make the previous acid halide halogen group to just eliminate, and then you can form the anhydride compounds. Okay. Let's do one more. Okay, I'll show you the. Let's try this one real quick. Okay. So. Okay. Can you guys try this one real quick? And maybe we can start from there. So it's not ester anymore, right? This is a propanoate. It's a carboxylic group with sodium propanoate. Okay, so let's do a little trick here. So whenever you see this one, I think what you can do is flip this one on this side. Okay. We just ignore the sodium. Okay. Okay. Just flip that inside, and then you just need to do, like I said, leaving group is gone, right? And this one. That's it. Makes sense, right? Yeah. Does it make sense? Okay. All right. So I can move on, right? So here's the thing. So whatever the carboxylate, those groups are going to the very electron poor carbon and just remove the halogen group. That's it. All right. Okay, so you can try to use some extra anhydride compounds to make some more complicated compounds. So in this case, what happens to here is you see this hydrox group on here in this. This is a salicylic acid. So we're gonna make the aspirin from this one. So if you can treat with some sodium hydroxide and water, which is kind of basic conditions, this will be deprotonated. Okay, so that means that this is an alternative to attack the that one over here. Because think about it. If you have this carbon, which is in carbonyl groups, and also in the hydrogen form, it has like an ethyl group like the formation, which is also withdrawing the electron from the carbon. So this is a very good target for deprotonated hydroxy group in base. Okay, so that goes to attack the over there. Okay, so that makes okay, and this O goes to right. This one. So this part is coming from here, and this becomes carboxylate because this is the negative charge. Okay? So this is become this one here. Does it make sense? So this is aspirin. This is what we did in the first lab. This. Okay, so let's move on. Yeah, of course. Just let me know if you have any questions. Okay, so maybe we'll do the same thing. Maybe can you guys try this one real quick? We have terahydroxyaniline with the maybe same acetic anhydride with some base condition too. Yeah, maybe try to use the same method, but on here, this amine groups, this the aniline groups, not the at this kind. The same trick, so you can look at this. And this is also the base, meaning they're gonna deprotonate the amine group also. Okay? So yeah, let's do this together. So the deprotonated, this carbon will be attacked, right? So it will be like. Here. This part is attached to this nitrogen with the deprotonation biobase. So that is acetaminophen. It's another medicine. I'll just move on because this might be this. Okay, so let's try to do ester. Okay, so we have if we have ester group compound, you can either treat it with the base, with the water, with some hydroxide, sodium hydroxide, or you can treat it in the acidic conditions. Either way is fine. So the product will be either going to have a carboxylic compound and with some alcohol. That is the basic form. So basically, it does the same. Either you do this one or this one. Okay. So what happens to here is that in a basic condition. So this is very similar to what we already done on Monday. We also did it with the acidic halide compounds. Only difference you have just have another living groups. So you had a halogen group to leave for previous sections. Here we just have this one to leave, but this one to leave and what? In this form. So when they protonate, it becomes alcohol, right? It's alcohol. So this is the only difference, but it's pretty much the same what we already did for the acid halide. So when you do the base, only difference is they approach as hydroxide anion. So when they make a push and push, negative, neutral, push, push. Okay, that's the rule. Okay. How about the acidic condition? Acidic condition is so they don't have much of a strong nucleophile yet. So that makes this that need to have a much poor carbon on here by protonating this off over here. Okay? This is the positively charged, and then water comes over here. So water takes this one as neutral, and then when this moving down to the here, they leave this one as well too. And then later, those will be also protonated. Yes. So become alcohol. So either way is fine. Either you're gonna have a water groups here, and later will take in the protons, or you can come with just the base, strong nucleophile. You can actually initiate the start the attack almost right away, or you can do it in a more indirect way. Okay? But the thing is, you're gonna have carboxylic compounds and also alcohol, because that you're gonna have different leaving groups and have that attack from a very strong base, which is the hydroxide anion, either water, later be deeper. Okay. So the bottom line here is whenever you have an ester group, when you treat with the very strong or acidic condition, will become carboxylic compounds plus the alcohol. That's the especially in acidic condition, because it has to be protonated. Okay. So let's do some problem. Okay. Does it make sense? Did I say too fast? Oh. I'll give you some example. So we can have some more practical sense how we can solve the problem. Okay. So we have this one. Okay. And then there you go. You can try it. Either way, it's a basic conditions, the sodium hydroxide or the acidic condition. We'll pretty much do the same. You're gonna have a carboxylic compounds with some alcohol, or carboxylate, depends on how protonate the compound your product with. Okay, about 30 seconds, we'll do this together. But try to make your own answer first and compare to mine, and it will make more sense. Okay. All right, so here's the thing. So like I said, this will leave, right? So meaning you just have to move it, okay? So I'm gonna do O, but this will goes to here because it's an electronegative element here. So this will become O, 2 carbons here, okay? Okay, so this is the, okay, so we're just gonna remove this one, and you just need to put hydroxy group there, okay? And this will be protonated, right? So we put, okay, so there's 2 product right there, okay? Makes sense, right? Just try to get this part off and protonate it, and just put the hydroxy group on the way you had the ether-like groups on ester group. So it becomes carboxylic compound from ester group, okay? Because you're changing this group to the hydroxy compound, hydroxy groups. Okay, let's do just one more and move on. Okay, let's do this one. Okay, the same, right? Same. about 30 seconds. It's pretty same trick we can do. Slightly different product, but same. Okay. All right. So yeah, we're gonna do the same over here, right? So we have this one over here. It's very different for carbon here. I'm gonna separate this one. So we do this one. You don't see it right, right? Okay. So I'm gonna remove this one. I'm gonna put away. Okay. I just do that. And then later we protonate it. So I'm gonna do. So this is a methanol. Okay. So methanol plus this one. Oxygen. Makes sense, right? I think, yeah, this is some trick you can do. But basically, if you look at the chapter 21, it's just the same mechanism all over, just having different groups on your carbonyl groups, which makes your different what? Carboxylic derivative form. That's the title of this chapter. Okay. So this is another one. So if you get the trick, it will become really a lot easier. So maybe this one is also pretty much the same. You need to have this one to leave and replaced by ammonia. But only thing you have to know is this will be once they attack there, because it's very little for carbon right there. So they always attack that carbon in the carbon groups. So then they have a positive charge over here, right? And that makes the push on here, okay? Over here, okay? And then once again, push down, push leave, okay? And then this will be taken by another ammonia. So there'll be ammonium cation, but it goes to that carboxylate compound, grab it, so it becomes ammonia again, plus methanol. Okay? So the bottom line here is this is also going to leave as the same. You're going to replace this the NH2, not 3, because that has to be also deprotonated another ammonia and give us also that groups. We take this one from another ammonium cation, so become methanol. So it's actually the same. We just had a different nucleophile. Because it's very electron point this carbon right there. In ester group. Does it make sense? Okay, let's try just one problem, another problem. Okay, so let's try this one. Okay, let's just try this one real quick. Okay, so got the trick right now. Okay. It's pretty much the same, right? Just different nucleophile. In my article. Does it make sense? You just you just need to have that groups to leave and replace with the nucleophilic nucleophile groups, but make sure deprotonate because once do it, it's the positive charge. But when it gets to the carboxylate after ether group like compound leaving the ester group, will be protonated by that, and there will be alcohol. This is not carboxylate anymore. So not carboxylate. The ether group like will protonate will become alcohol. So alcohol side. So let's move on. All right. So maybe I think maybe you can try this one too. Maybe R. Say about another ester group. treat it with the lithium aluminum hydroxide. Here. Okay, so it's pretty much the same. You're gonna have those two hydrides added on from this lithium aluminum hydride, and also you're gonna have alcohol, okay, which is similar to what we had for acid halide, but once again this is a different group. So that is why this will become. You're gonna also have another product which is HOR, which is also alcohol. Okay, so same, but so same that we did for acid halide compound. You just had to make that halogen group leave the two hydrogens. Replace this one by the protonated, so it will be alcohol, the hydroxy group here. Beside that, because this one is also once it leave and protonated by this one, and so it will be alcohol. So only difference is this will become not making this the metal halogen salt, but actually they makes another organic product which is alcohol. Okay, so so this is just do the same thing over and over and over. Whatever the ones on here with your carboxylic derived compounds that makes up with the hydrogen with the cation. So that's it. Okay, so let's. I think we have some idea, but let's try the quick problem still. Okay, let's try this one real quick, and we'll move on. Okay, so almost same as the acid halide form. Just have a two hydrogens on that electron probe carbons again, and the ethoxide form will become protonated, become alcohol. Okay, so that's the thing. But mainly, if you can get the main product beside the alcohol, it will be just fine. Okay, about 20 seconds, we'll do this together. Okay, so yeah, so basically this will leave, right, and protonated, so it's ethanol, and this will become protonated, okay, and so I'm just gonna write it in more general way. This one, so it's the same thing, just the rotating a single bond. Okay? So where you had a carbonyl group will be protonated, become a hydroxy group. So I just flipped it in this way because it's a single bond, so it doesn't really matter. It's the same thing. And you have that the alkoxide form protonated in alcohol. It's just same thing over and over and over, just different nucleotides. Okay? Different reagents. Okay. Does it make sense? Can I move on? Okay. So then, is the case we have other one. You can try to. So this is a way actually you can keep the carbonyl groups here with the ester group. We can treat it with the di-isobutyl aluminum hydride, and then some acidic condition. Okay. So in this case, what happens is they don't actually do remove the carbonyl groups. They keep it. Okay, so, and you just need to stop at the aldehyde form, which was previously an intermediate we don't normally see, but they stopped there keeping the carbonyl group here, which is aldehyde, and this have the protonated alkoxide, which is also ethanol. So in this case, you can actually keep your carbonyl group there, not even further reduced by to be alcohol. Okay? So this is something you can do if you don't want that to happen. All right. You want to try this one too, or can I move on? Okay. Okay. So how about this one? Let's try. Can you guys try this one real quick? And think about this is also same mechanism you're gonna do. Okay? With the one we already did for the acid halide form, this is the ester, but let's try to do the same thing what we did for the acid halide compounds. Okay, one might be. Okay, so another green R. So make sure this will be. Yeah. This is almost the same as what we did for acid halide form today, but just the different group here, which is ester group, whole and as a whole, but it's pretty much the same. You can try to there'll be two, like it did for the previous one. Okay, so yeah. So in this case, you just need to have this one move. Okay, same. And then instead of two hydrogen like you did for the aluminum, they just have two R groups. And this will be so this is what we did with the other compounds, but the same. It's just a different carboxylic derivative compounds, which is ester now. But it did it pretty much the same, just you had a different leaving groups. Okay. You wanna try one more? Can I move on? One more?
No, you can move.
Oh, one more. Oh, I can move on. Yeah, good. Okay, so that's good because now we get to the last part, which is kind of a tricky in the mechanism-wise, but I think you would love it because once you get the trick, it's actually very easy. So the last part is amide. So if you have amide, you can treat it with the lithium hydride again. Some water. So basically, what happens is when they do the hydride, this is kind of something. So you had this one here, right? You had this one over here. So if it was a acid halide or acid groups, another, we had this group leave, right? And then replaced by two hydrogen whenever you do this one, okay? But this is kind of exceptional, okay? So for this one, only thing you have to do is this one. So this will not leave. This is the one this is one of the carboxylic derivative compounds that whenever you treat with this lithium and aluminum hydroxide, that will not leave. Can you guys remember, can you guys guess why, based on what we learned in Orgo 1? So the samine group on this amide is very poor leaving group, so that's why they're not leaving. Okay, so what they do is when the hydride comes over here, they push onto the here, but now they pair up with the lithium first, okay, and then later they switch it to this one. When the hydride is coming there, so it's neutral. So when they're coming in as these two salt, that goes to the one hydride from here, because that's why you have a hydrogen bond to here. So push, it goes to there. So this is become what? Aluminum hydride, which is a 3. But this goes to the negative over here, okay? And then this this lone pair on this nitrogen goes to there, and they leave. So that means this is a positive charge. Is only one hydrogen here, but another hydride coming in from this compound, the negative charge, it pushes it. So there will be two hydrogen added here now with a single bond. This is neutral now. Okay, so basically, the simple trick you can do is whenever you have a amide, just this is the trick. So in this case, you're not gonna have this one to leave because it's very poor leaving group. Instead of this one leave, they make this replace the carbonyl group without alcohol hydroxy group. That's how poor the leaving the amine group is. Okay? Does it make sense? Okay. So let's do one problem and move on. So I mean, the exam problem wise will be even easier because you only need to remove the oxygen. Okay, let's try to do this real quick. So like I said, very simple trick. Just remove one and replace them by two hydrogen. Okay. Okay, but 30 seconds. It's pretty easy, right? So just copy everything, okay? And then just keep the rest. But you just had a two hydrogen removing this one, but you can always imply the hydrogen, so just remove the oxygen, carbonyl groups. That's it. That's all you need. So in this case, it's exceptional because you're gonna still have amine groups on the amide still there, so it becomes just stay there. So it's different from the other case. So I will stop here. So